Concrete. It's the literal foundation for nearly all modern buildings, everything from sidewalks to townhomes to skyscrapers and bridges. Concrete is one of the most important engineering materials known to mankind, and at times concrete must withstand incredible tons of pressure as well as endure extreme elements from the weather, whether that be snow, ice, water, heat, whatever it may be. Currently, compression strength is the determining factor for the quality of the recipe. Failing to correctly mix and process the concrete could lead to catastrophic consequences. In order to test the compression strength of the concrete, engineers must first create small batches of concrete cylinders with different combinations of the raw material, and then test these cylinders with the given strength variations. It's recommended that they wait about 28 days in order to get accurate results, so it can be extremely time costly. But what if there was a way that we could predict compression strength with machine learning? Well, that's exactly what we're going to do in this video. We'll be using concrete data I found at UCI. I'll link that in the description. I was inspired to do this project after coming across this data, but I never really felt comfortable tackling it until I read some other Jupyter notebooks, especially by the gentleman who goes by Prane Modukurus. Probably butchered his name. I'm sorry. I doubt you'll ever see this video, but for the viewer, if you want to go check out how he approached the problem, I'll leave a link to his Jupyter notebook in the description as well. Enough of this. Let's go ahead and jump in my computer and get started. All right, so we're going to get started here. Like with most things, we need to import some packages that will help us accomplish our mission here. Namely, we're going to import NumPy, Pandas, Matplotlib, and Seaborn. So because I do that all the time, I just keep it handy and copy and paste it here like so. And then we're just going to go ahead and run that. Next thing we'll need to do is gather our data. So the way to do this is to just set a variable that is the path string, which looks like this. And then from there, we can use pandas read Excel. And I usually like to put that in a variable as well. So we'll do data equals pd.read Excel, and then we'll pass through our path there. We'll run that. Excellent. And now let's just go ahead and take a look at our data. So as you can see, the column names are very long. We want to make that a little shorter. So one way we can do that is to map new names into these columns. So we're going to set a new variable with our new column names in a list. We're going to set another variable with our current column names. So let's do current column names equals list data.columns. Now I'm going to write a for loop. So for I name in enumerate current column names, we're going to map, excuse me, forgot something really important. We need to actually include a dictionary with our map in it. So we're going to map the name, the new column names in I. Let's go ahead and run that. And now let's change data equals data dot rename columns equals mapper. And then now let's check our, and we have shortened our column names. So basically what we did here is we created an empty dictionary, and then we went through with a for loop, enumerated our current column names, which we made into a list here, and we put these names into the mapper, and we equaled it the new current name. So it went through each one, and for 1, it made cement, and for 2, it made blast furnace, and for 3, it made fly ash, right? Because we are enumerating out the current column names, mapping it in here with the new names for each one. Hopefully that makes sense. Next thing that's really good to do in cleaning up our data and processing it is to make sure that we aren't missing any values. So data.isNA.sum. Oops. And as you can see, we have nothing missing. And they're all in integer 64, which is great. So that just about does the cleaning and wrangling of the data. So the next thing I like to do is create a scatter plot for each feature of our data against the target variable column. And we can do that using a for loop. We'll type for features in data.columns, and we'll plot a scatter where the x equals data feature, and the y equals our target variable. Be sure to spell everything correctly, otherwise it will not work and give you an error. And just to keep things organized and sort of just looking good, we'll label, it's also just good practice to label our axes. And we want to show it. So let's see if that works. It did not because I misspelled feature. And there we go. You can see this is our cement strength, right? And this is our feature here. You can see that there's a good linear correlation with that one. It's pretty difficult to see if there's any linear correlation with this one. Also difficult with fly ash. With water, it looks like there's a negative correlation there. With superplastizer, looks somewhat like linear correlation. Again, difficult with core sag, but you can see here how useful this is. And of course, with cement strength and cement strength, it's obviously going to have a one-to-one correlation there. But let's say we want to actually see what the correlations are. One thing that we can do is go ahead and create a heat map, which is another cool feature of Seaborn. Let's create a variable called core, and that's just data.core. Core stands for correlation. And in order to call a heat map, we'll just call SNS heat map. And our first data point is correlation. We could just call this here. Let's see what happens. And you can see we have our heat map. And it's pretty cool. But it would be nice to see what the actual numbers are on the correlation here. So we can do that by calling annot. For annotation, we'll call true. And you can see we have the numbers here, which gives us a good idea of what the correlations are. One thing I also like to do with heat maps is it can be kind of hard to tell what correlates and what doesn't correlate, even with the annotations and even with the different colors. these dark or negative correlations stand out a lot more than maybe the positive correlations here. And it can just sort of look like you're looking at just, I don't know, more of a plaid color. So what I like to do is create a color palette that will help distinguish what correlates and what doesn't correlate. There's several ways to do this, but you can call CMAP, and my favorite one is cool warm. And there we go. So the blue is negative correlation and the red is positive correlation. So as you can see, there's a lot more features that negatively correlate to one another than there are positive. And when it comes to our compression strength here, we can see that cement, superplastizer, and age in days have positive correlations. And then we can see too that the superplastizer and the water have a very strong negative correlation. So yeah, the cool warm, in my opinion, just makes things a lot easier to see what is correlated and what isn't correlated. If this is a little small, the other thing that you can do to make it a little bigger is just increase the figure size. So the way to do that is you can do PLT, fig size. Actually, it's PLT figure, fig size, and we'll do 9 and 7. Let's see if that works. Yes, it does. Okay, cool. So it just increases the squares and makes it a lot easier to look at. I think that just about does it for our exploratory data analysis. We sort of have an idea what correlates to positive or stronger compression strengths and what doesn't. It's the cement, superplastizer, age and day. We know that superplastizer and water create a negative correlation to it. Let's go ahead and move on and start training our data and pre-processing it. In order to do that, we'll need to import sklearn, model selection, train test split, and we'll do pre-processing as well. Let's load those guys into the Jupyter notebook. And then let's go ahead and we're going to start with the linear regression models first, I think, or just several different types of regression models, actually. So we're going to need to split the data. We also need to scale it. So let's go ahead and create C equals our scalar. That's our standard scalar. Make our x train is equal to sc dot fit transform x train. We're going to do that for our x test equals sc dot transform x test. So basically, let me break down what we're doing here. We're splitting up our data. The x is going to be our data with everything excluding our compression strength. And then our y data is going to be our target variable. So our y is going to be nothing but our compression strength. We're going to split that up into x train and x test, y train and y test using the train test split from the sklearn model selection, passing through our x and y's. Test size is going to be 20%, and the random state is going to be 2. We need to scale our data, so I just created a variable here with the standard scalar from our sklearn preprocessing. And then we called sc.fitTransformXtrain and sc.transformXTest. The reason we're not going to scale our y's variables is because we want our model to accurately predict untreated data, right? We want, based on what we found here in our x, to correctly predict what we find in our y when we haven't done anything to it. So we're going to call that. And I don't plan on these regression models doing much, simply because just having a look at our scatter plots over here became pretty, like this doesn't seem to have any linear, neither does this or this a little bit. This, definitely some, sure. So basically what I'm trying to get at is I'm guessing our random forest or our decision tree models will work better, but let's go ahead and go through the regression models anyway. There's 3 that we're going to go through: linear regression, lasso, and ridge. In order to get those, we're going to use another package from sklearn. So let's just go ahead and copy and paste that in. Let's go ahead and make variables of these guys. And then we're going to want to fit our data set here, our X trains and Y trains and X tests and Y tests. So I'm just going to go ahead and copy that in. It's pretty simple. You just call the variables that we made and then pass through X train and Y train, X train and Y train, et cetera, et cetera. From there, we're going to go ahead and call our predictions. So let's go ahead and do that. So Y prediction linear regression is going to be lr.predict x test. All right. And let's go ahead and run that. Something went wrong with ridge. What did I do? Ridge should be capitalized. Excellent. Okay, great. So we have our predictions here stored in these variables. So let's go ahead and take a look at them. This is going to be a little tedious, but it is definitely worth it. I've already done the work, but I'm going to go ahead and copy and paste it here. If you want to pause the video, feel more than free to do so. But basically, oh, silly me. What I do need to do, though, is in order for this to work, is we need to create some good old figures. So let's go ahead and do fig ax1 equals plt subplots. And let's go ahead and put in some good old-fashioned customizations here. We'll do 1, we'll do 3, and we'll do fig size equal to, want to be able to make sure you guys see it, so we'll do 12 and 4. We can adjust it later. Hopefully that works. Let's go ahead and see. It did not work. What did I do wrong? Oh, you know what? Maybe I need to... Do we need to go ahead and do all of them? If I just got rid of this. And there we go. You can see with our linear regression, this line here is the true 100% predicted. And these points here on the y-axis is what's real, and on the x-axis is what's predicted. And the closer it is to the line, the better the model is performing. We didn't just do linear, we also have lasso and ridge. What we can do here, though, is basically repeat what we just did for the other two. AX2 and AX3. Be a good idea to wrap these in parentheses. We'll go ahead and say call 3 of these bad boys. And then we're going to want to recreate AX1, but load in, instead of Y prediction LR, we'll want to put in, Y prediction lasso and Y prediction ridge. I've already set that up in ahead of time, and so I'm just going to go ahead and copy and paste those bad boys in. Let's run it again. Hopefully it works. It did. All right, so we can see ridge and linear worked about the same. I mean, they all work just about the same. They're all, it looks like they all work pretty well. It kind of looks like the ridge and linear look more closer together than lasso. All right, but you know what? I think we can do even better by by using some different models, basically. I want to use a decision tree as well as a random forest model. So the first thing we'll need to do is import those. So from sklearn.tree, import decision tree. regressor. That'll look like that. And then what we'll do is create a variable that stands for that. DRT sounds like a good name. That way we don't have to type that out every time we want to use it. Excellent. And now let's go ahead and fit our data. So DTR, oh, let's go ahead and fix that. DTR dot fit X train Y train. Now let's make our predictions. Y, that's going to be too long. Let's just do Y pred DTR equals DTR dot predict X test. Next thing I want to do is see what it looks like. We can do that by doing what we did above with our linear models here. And it obviously did not work. Why not? Oh, because I misspelled. There we go. As you can see, the decision tree already has a much closer grouping on the line than any of our linear, lasso, or ridge models. But first, let's also check out our random forest regressor as well. So it's going to be pretty much the same thing that we did above. We're just going to change, variables. So instead of decision tree regressor, we're going to type in random forest regressor. So that's, and we'll do that for here too. And come to think of it, we probably shouldn't call it the same. We'll call it RFR. And let's go ahead and run that. I got an error. That is because it does not come from tree. It comes from ensemble. Let's try that. It worked. And then again, we're just going to copy this, but we're going to change our variables to match what we're doing here. And I would say even a tighter fit. Yeah, I would say even a tighter fit. One thing that we can do though, in order to, the random forest regressor here is probably our best performing model here, just based on what we can see visually. But, it helps to have things numeric in value so that we can see what's going on. In order to do that, you can look at several different metrics. We'll have to import some good old-fashioned metrics from sklearn.metrics, import mean squared error, mean absolute error, and R2 score. At this point in the tutorial, you can definitely skip this if you don't want, because the next bit is quite tedious. But basically what we're going to do is print out, I'm just going to print out the mean squared error, the mean absolute error for all of our models here. The code looks like this. So these are for the regression models, the linear regression, lasso, and ridge. Yeah, I was right. The linear regression and the ridge regression are 10.29. Lasso regression is 10.68. The lower this number, the better performing the model. So let's go ahead and take a look at the metrics for random forest and decision tree. It's going to look exactly like this, just with these two models instead. That's our decision tree. So there we go. Yeah, you can clearly see the random forest regressor here is the clear winner. Its root mean squared error is the lowest, which means it's the best performing model to predicting concrete compression strength given our variables here. All right, there you have it. We predicted the compression strength of concrete using machine learning. Anyway, I hope you learned something from this tutorial. Let me know in the comments if you'd like me to try a different project that you're more interested in. But in the meantime, Be sure to learn, apply, and thrive. Bye.